Hello and welcome back, and in this lesson we will derive the wave velocity using Newton's second law. And for this, let's consider a single symmetrical pulse moving from left to right along a string with a constant speed v. Now, for convenience, we're going to switch our perspective. We'll choose a reference frame in which the pulse remains stationary. So imagine you're running right alongside the pulse at velocity v, keeping it perfectly in view. That is, to you, the pulse isn't moving at all. It's just sitting there. But here is the critical part. While the pulse looks still to you, the string itself is now rushing past you. Because you are moving forward at speed v, the string appears to be sliding backward at that same speed v. It's exactly like looking out of the window of a fast moving car. The road isn't moving relative to the ground, but relative to you. It's sprinting backward. Okay, let us zoom into a very small string element of length delta L within the pulse. We will assume this element forms an arc of a circle of radius r and subtends an angle 2 theta at the center of that circle. Now, think about the forces at play here. One, I see a force T, that is the tension in the string, pulling tangentially on this element at each end, and the other is the weight mg of this element, which most textbooks don't show, and rightly so, because the weight mg here is significantly smaller than tension T. And if you're curious, I've shown the calculation that proves the point in the description below. And if you look at the geometry, the horizontal components of these forces actually cancel out, but the vertical components add together to form a net inward force F. In terms of magnitude, we can write this as force is equal to 2 times T sine theta. Now, you might notice in our diagram that the tension forces don't appear to point directly towards the center of the circle. Well, this is a deliberate choice for visual clarity. While a derivation relies on the assumption that the angle 2 theta is extremely small, we've drawn it much larger here so that you can clearly see the vectors. In reality, as you make this angle significantly smaller, shrinking the element delta L towards a single point, the horizontal components cancel and the net force converges perfectly towards the center. And if we take the small angle approximation, that simply says that for small angles, sine theta is equal to theta in radians, what we get is F is equal to T times 2 theta. And since the length of this arc is nothing but a product of radius and the angle in radians, we get F is equal to T delta L upon R. Now, let us say the linear density of this string is mu. That can be calculated simply by dividing the total mass of the string by its total length. So it is nothing but mass per unit length, and then the mass of this element can be written as delta m is equal to mu delta L. Now, at this moment, the string element delta L is moving in an arc of a circle. This means it must have a centripetal acceleration directed towards the center of that circle, defined as A is equal to v square upon r. And we take the element's speed along the curve as approximately equal to v, which is essentially the string's backward speed in this frame. And this would hold true as long as the slope here is small. That you can see it is. Now, let's put it all together. We have the force, the mass, and the acceleration, the three essential elements of Newton's second law. And combining them in the form of force is equal to mass into acceleration gives us T delta L upon R is equal to mu delta L times V square upon R. And we can see the delta L and R terms cancel out, yielding V is equal to under root T upon mu. So this formula gives the speed of our pulse and importantly the speed of any other wave on that same string under the same tension. Interestingly enough, this leads us to a vital conclusion. The speed of a wave along a stretched ideal string depends only on the tension and the linear density of the string. It does not depend on the frequency of the wave. The frequency of the wave is fixed entirely by whatever generates a wave, like a person moving the end of the string. And for a sinusoidal wave train, the wavelength gets fixed by the relationship lambda is equal to V upon F. So remember, just because you can increase the frequency of motion here by, let us say, moving the hand more rapidly, it does not mean that you can increase the velocity, simply because velocity has no dependence on frequency. So when you watch a guitarist tune the instrument, you are witnessing Newton's second law in real time. By tightening a tuning peg, they increase the tension T, which directly scales the wave speed V and raises the pitch or the frequency. Similarly, the reason a bass string is heavy and thick is to maximize the linear density mu, keeping the wave speeds low enough to produce those deep resonant frequencies.